On this slide, you will see various project management entities and terms defined. On the subsequent slides, you will see examples of each. Now that you've seen the entities and the notations by which that you could use to create a project plan, that you could use to do your planning, the question now is, what activities do you put on these charts? What do you put on the project schedule? What might you create an activity breakdown for, and so on? Well, for a software project, you would begin by looking at the stages of a software project, which are the inception, elaboration, construction, and transition stages. If you're in inception stage, you would take the things that you have to do in that stage, such as create an approximate vision, develop a high-level business case, create some high-level estimates, and so on, and you would put them as steps in your project plan. Then you would create a section for the elaboration phase, and there you would put in tasks for refining the vision, defining the architecture, prototyping the difficult or risky elements of the architecture, and so on. And then in the construction phase, you would put essentially the features that you would release in each release within that construction phase. And then within the transition phase or transition stage, you would put in things like beta test, customer handover, user acceptance test, things like that. Once you've identified the activities, you then have to estimate them. Basically, you have to figure out how long they might take, how much they might cost, how much these activities might cost, and so on. So now let's look at a set of estimation techniques. Just for completeness, let's just note down why we estimate as opposed to, I guess, measuring. In a software project, the project doesn't exist, the system doesn't exist, the object doesn't exist. So therefore, you have to estimate something that will be there in the future. The other reasons for estimation, not necessarily in software project management, but just the reasons for estimation is that the object that you'd like to measure is inaccessible. So, for example, you might have to estimate the size of the moon because you can't reach it. And the third reason is that direct measurement is too expensive or difficult. So, for example, if you wanted to measure the temperature at the core of the sun by sending a spaceship there, going into the core of the sun and measuring temperature there might be too expensive or too difficult. Therefore, you've got to estimate it. So the standard way of dealing with all these three issues is essentially to identify proxies for the real metric that you want to measure. So you measure something else that allows you to estimate the size of the thing that you really want to measure. Okay, so that's the goal in all of this. Now keep in mind one thing about the nature of estimation, in particular the nature of estimation in software projects. The first thing is that the estimated amount in general increases over time. It rarely reduces. Why might that be? For example, if you just took something, you were estimating something and it followed your estimation followed a standard normal probability distribution, you would think that you would estimate low as much as you might estimate high. But in software projects, that never happens. You always, as the project progresses and you get better at your estimation, and we'll talk about why estimations get better over time, the size almost always grows. It rarely shrinks. Here's why. The reason for why the estimation always increases is actually software engineers and engineers in general are usually pretty good at estimating what they do know. So when they have to estimate a project, they might look at its components, or they might look at its complexity and provide an estimation of what it might take, how long it might take, or what it might cost. Well, they're doing it based on what they think they know about the project at this given time. And if the project runs into any unknowns, which of course these engineers don't know at the start of the project, well, these will cause increases in time. They will not cause decreases in time, because nothing that you think will be in a project ever goes away. You still have to do those. It's the new things that get added onto the project that add to the estimation, okay, or that add to the cost and duration. So always keep this in mind. You'll rarely run into a situation where your estimation reduces over time. You'll typically run into, you almost always, your estimations will increase over time. The next point about the nature of estimation, once again in software projects, is that the uncertainty in estimation reduces over time. And this is the reason for this is pretty obvious. As you go through a project, you know more about it. Things that you were originally estimating because they didn't exist now exist, and now you can measure them, and you can use that to validate your prior estimations, or use as the foundation for future estimations. So basically, over time, you start to know more, and therefore the estimation uncertainty, the variation in the estimation, will reduce over time. We show an example of this on the next slide. And finally, the greatest predictor of successful or correct estimation is having done that kind of project before. So for example, if you've built a website before, then your estimations with respect to the next website that you want to develop will be more accurate than if you haven't built a website before. Once again, the reason for this is pretty obvious. If you've done it before, you have a sense of what it might take, therefore your estimates are likely to be better. This picture illustrates what I said on the previous slide, which was the fact that the uncertainty in estimation reduces over time. This picture is also known as the funnel curve for estimation, or Barry Bame's cone of estimation uncertainty. And the idea behind this picture is that as the project progresses from initial concept through approved product definition, through requirements complete, user interface design complete, detailed design complete, and finally software complete, the amount that the actual time it took, or the actual cost, or the actual estimate was different from what was the actual time that it took was different from the estimate of the time that it took. That variability will reduce over time. So at initial concept, you could be as low as a quarter. Your estimate might be 4 times too low or 4 times too high, and then obviously when the project finishes, that uncertainty in your estimation will go to 0, because when the project finishes, your actual time is essentially your estimate. Okay, but and as you go through the various milestones in the project, and your estimate will be more and more based on fact, and therefore the variability in that estimate, or rather the variability in the difference between the actual time or effort and the estimate, that variability will continue to shrink. So in order to do your estimation, what can you use? What parameters do you use for your estimation? Well, you can use the problem, a description of the problem, and any requirements that you might have of the software system. You could use that for the estimation. So for example, you could look at the problem that's being solved and think about whether the software system that is going to be built in order to solve that problem is simple or complex. And if it is a complex software system, then in your imagination, if it is a complex software system, you would add more time to your estimate. Similarly, if you could see the list of use cases, you could go use case by use case and get a sense of what implementing each use case might take, and you can add them all up and use that for your estimation. So in those two cases, we used a definition of the problem and the requirements of the system to do your estimation. Well, you can use the structure of the solution as well to do your estimation. So for example, once you have the architecture of the system defined, and we'll talk about architecture in later lectures, but for now, assume that architecture is the components that will be needed that the system will be composed of. Once you know that architecture, you can perhaps use that to do your estimation. So you could see how long each component might take to implement, and use that and add them all up and use that as your estimation. Note the difference here. In the previous case, you were using a description of the problem and the requirements to do your estimation. Now you're using the definition of the solution to do your estimation. And finally, in all of this, you might throw in some kind of quantification of uncertainty. So if you're early in the project, you might say, you might add a pad of maybe ×2. Later in the project, when you have the architecture defined, maybe you'll reduce that padding from 2 to 1.5. That's sort of what we mean by a quantification of the uncertainty. Next, what is the process of estimation? So you can, here's how you typically go about it. You consider the steps that you would take to produce the project. In other words, you would consider the software development lifecycle. You would take a look at your project schedule and say, these are all the steps I need to do. And then you would estimate each step, and you could add them all up. While in your estimate of those steps, you would consider the capability of the resources. So if you have an expert team, an expert requirements team that has done requirements analysis many times, you might say that you might reduce the estimate for a particular step in the project, which is the requirements collection step. On the other hand, if you have a team that has never collected requirements before, you might increase the time needed for requirements collection. Similarly, if you have an expert architectural team, you might reduce the time for doing the architecture. If you have a team that's doing this kind of big system for the first time, you would increase the time, and so on. So this is what we mean by consider the capability of the resources available. And of course, you have to consider the cost of the resources available. So because part of estimation is effort, and the second part of estimation is cost. So you estimate higher if the resources you are using, both personnel resources as well as computing resources like systems and so on, were more expensive. The third thing you would consider in your estimation are constraints. So where is the software being developed? Do you have a working environment with all the necessary, for example, connectivity and so on? Is the project an outsourced offshore project? You would factor these kinds of constraints into your estimation, and then you might add some additional steps. So there are steps that are directly contributing to the project, basically like your core value chain activities, and there might be secondary activities that are not directly contributing to the development of the software. So for example, you might be doing some risk mitigation. Incidentally, we will cover risk mitigation later, but let's say you do certain things to reduce the risk in your project. For example, you train your software developers on Java because this is a Java project and none of them know Java. Well, that isn't a primary step. That's a secondary step in your software development lifecycle. So make sure to count all those secondary steps, like training, like risk mitigation, into your estimation of the project. So what is the problem with estimation in software projects? The problem is that you're trying to do an estimate early in the game because you want to have a sense of the budget, the cost, you want to report that back to your customer, you want to have all your resources in place. You want to have all of those early in the game before you actually have anything. And that's the basic problem with estimation. And things change. So what things change? The features that might need to be added to a project may change. The people who you have on the project might change. Some might leave. New people might come on board. Things like that. Thirdly, any kind of measurement adds cost. So if you go through a planning session to estimate and measure how much work something might take, that in itself adds cost. And because software is complex, trying to get a sense of it in order to estimate it is going to add cost as well. The fourth thing is that software is intangible and invisible until actually finished. Requirements are imprecise, the notations are poor, they don't capture requirements exactly. Acceptability depends on the taste of a customer. So the customer may say, I need this feature, and you might think it's a simple feature, but the customer might be a might really be thinking of it in a more complex way, and therefore the feature might actually cost more. Um, Next, individual productivity varies widely. So a study once showed that experienced programmers are 6 to 10 times more productive than inexperienced programmers. And um, this variation in developer capability is huge, and you cannot, just by interviewing the people working on your project, know whether they will be productive or not. You just, you only know once they have begun working and you have some familiarity with them. The next reason is not enough time is spent in estimating a software project or in the planning of the software project. What typically happens is that the projects are under pressure to keep working, and thinking is considered a bottleneck, and essentially not enough time is spent. Next, and this is a great illustration of why software estimation is difficult. A software project is like an iceberg. Only a small portion of it is above the water, and the larger portion of it is below the water, and you're trying to estimate what's below by being able to see what's on top. Okay, so all you can see, for example, are the end user functions, the use cases, and you're trying to estimate from there what all steps you might have to take with respect to the process, the development steps, the support steps, the installation steps, and all of those, those steps are going to, result in maybe thousands or tens of thousands of lines of code. So, 10 end user functions might result in 100,000 lines of code. The 10 user functions are the tip of the iceberg visible above the water, and the hundreds of thousands of lines of code is the rest of the iceberg underneath, and you're trying to estimate the whole iceberg from what you can see above the water. And the last thing is that causality in a software project is often hard to figure out. So when there is a delay, you don't know why there's a delay without expending a lot of effort to figure things out, especially if you have a large team. One person may hold things up. You might not even know there's a delay until a few days have passed, and then tracking back through everybody's memory and chasing things down and figuring out why a delay occurred might be difficult. A bug might be complex to fix. A bug, or the bug might be simple to fix, and the person assigned to fixing the bug simply did not have the knowledge to do so, etc., etc. Essentially, finding the root cause of the delay or the variation in productivity is difficult to find. Now, here's the second problem with estimation of software projects. The problem is that when you find out about the true cost of something varies based on the stage at which you find it out. So, for example, if you find out that you need a new requirement and it's still in the requirement stage, all you need to do is add on another use case, and you can throw that into your estimation. But if you find that you need a new requirement when you already, say, for example, release the software, then not only do you have to add that requirement and build it, but then you have to, the cost of including that requirement is much higher because there are already pieces of software built. If that new requirement changes things with respect to the architecture, there's a lot of work to be done to break the architecture apart and incorporate this new requirement, fit this in with all the stuff that has gone in there. So basically, if your estimations are wrong, if your estimations don't include some element of the system or some element of the project early, the change in estimate, the change in effort or cost is huge if you discover that new problem or that new feature or that new issue later as opposed to earlier. Now, one thing to note is that in structured projects, rather projects that use structured methodologies, this cost, there is a rapid climb of the cost per phase. So if you're doing, say, waterfall, then the change in the cost for including a new feature or fixing a new issue is, climbs rapidly when you go out of the requirements phase into the subsequent phases and so on. However, when you do iterative and incremental, the rate at which the cost increases, even though that's a structured methodology, the rate at which that cost climbs, depending on when you discover it, is less. And when you do agile, simply because you're doing so many iterations um, and validating each requirement and so on as you go, the the rate, there is a slower climb with respect to the cost of a change, depending upon when you find it. Of course, it still doesn't mean that agile is by definition better than structured projects, simply because even though the way, the rate at which the cost of a new feature increases, depending upon whether you do it in and figure it out in an early iteration or a later iteration, or early release or later release, there are many more releases and iterations in agile. So you have you have many more features allowed or discovered earlier. So even though the climb is not as high, you're doing many more releases, and therefore the cost might still be high for incorporating all those features. So how do we address all these problems? Well, the first is a change in philosophy. So rather than measurement in order to predict, the idea is that you measure in order to monitor, control, and recover, rather than trying to predict exactly how something might take, how long something might take. Okay. The second way of dealing with these problems is to estimate in a disciplined manner. So don't just hold a wet finger up in the air and in the wind and estimate based on that the power and direction of the wind, but estimate in a systematic, disciplined manner. Understand the requirements. Choose the process. Understand what work products you're going to create. Break the problem down into smaller components and estimate based on that. Secondly, use a mix of techniques. So if you remember, when we did the business case for the project with the high volume law firm, the technique we used to do the estimation was basically a resource-based technique. We assumed that there would be a team lead and say 4 developers to do this project for a year, and we estimated based on the cost of the developers. Well, that's one way. Now correlate that estimation with by listing all the use cases and estimating what it would take to implement each use case, and compare that method, that estimate with the first estimate, things like that. And thirdly, while as you do the estimation, record the assumptions under which you're doing those estimates. So for example, if you're estimating based on resources, then record the assumptions you're making about the capability and quality and number of the resources. So if any of that changes, you have to adjust your estimate. Yeah. And this is what is all that is done before the estimation is made. In fact, at the kickoff points for the project and for the various iterations and releases of the project. Now, during the execution of the project, during the iteration, during the release, as the work is being done, collect the actual. So collect the actual time that is being spent, collect the actual cost that is being expended, and use that to compare against your estimates and try to understand why there are differences. And then secondly, as you finish an iteration, take the actual numbers and use that to calculate your overall cost. So at every iteration, or as you collect information, you're replacing estimates with actual numbers. So your final estimation, your total estimation, is reducing in uncertainty, because more and more of it is based on fact as opposed to estimates. Other couple of things, watch for violations in estimation in assumptions. We talked about that. And watch for changes in key factors, either the process used or the requirements or the environment, all of those things. Watch for those. And then after each project, and in fact after each step in the project, collect the actuals, compare against estimates, analyze why the estimates were different from the actuals, and then very importantly, calibrate the estimation so that you can improve over time. So calibration means If you see one use case and you had estimated 5 hours of work, but your actual time was 8 hours of work, when you now know that a use case of that complexity takes 8 hours, so the next time you see another use case of that complexity, estimate 8 hours, not 5. Yeah? This is known as calibration. So we talked about estimating in a variety of ways, and there are basically two basic types of estimation, linear and parametric. So linear estimation simply means break the problem or the solution up into parts, estimate each part, and then add them all up. So for example, a linear estimation for a project might simply take each use case, estimate the amount of time needed for each use case, and just add them all up and say, here's my estimate for the whole project. The question, of course, in this is, can you assume linearity? So do you simply add all the individual estimates up, or do you maybe add the first and second use cases up, but then when you do the third use case, you multiply it by a factor that sort of factors in the complexity of adding a third use case when the first two have already been implemented, things like that. But anyway, all these techniques where the problem is broken up into its individual parts and then estimated, and where then the individual parts are estimated, and then the total is found from that, the individual estimates. That's known as linear estimation. The second kind of estimation is parametric estimation, and the final estimate is a formula that is applied to various assumed or visible parameters of the thing that you're estimating. So for example, in a software project, you might look at the parameters of the product that you're building, or the process that you're using, or project parameters such as number of stakeholders and the quality and experience of the team and the schedule that you've been asked to work under, and so on. So let's take the example of baking a cake. So a linear estimation would an example of using linear estimation to estimate how long you might take to bake a cake would be to look at the recipe, estimate each step in the recipe, and just add up the effort for each step, and to get the total estimate for baking the cake. The parametric technique would involve estimate the complexity, do your estimation based on the complexity of the cake. Is it a multi-layer cake? Does it have complicated ingredients? Does it have complex components such as the icing? Take those kinds of parameters and plug them into some kind of a formula or function, and estimate the effort of the cake based on that. So in your handouts for this section, you will see a paper on use case points estimation. That is an example of parametric estimation, and you're actually going to be asked to use that in your project. Okay. So now the question, the final question is, where do you get the data to do your estimation? So for example, if you're using linear estimation, how do you know what to estimate for each step? Or if you're doing parametric estimation, assuming you're taking various parameters, converting them into numbers, and then plugging them into a formula with coefficients and adding or multiplying them all together, where would you get these numbers? Where would you get the coefficients? Where would all those come from? And the best answer that the software engineering community has come up with, the software engineering research community has come up with, after many, many years of research dating back to the late 60s and early 70s, is that you need to collect data about your organization, your team, your company, and use that to derive these coefficients. Okay, so historical data provides the value of these coefficients. Now, there is actually quite a bit of historical data available across, for example, projects in the defense industry and so on. So there are some industry-wide benchmarks available for these kinds of numbers. And you can start there. But organizations that have success in estimation typically over time collect data and use that to make their estimation process better and better and better. So the previous slides talked about how to do linear estimation, what to measure, what calculations to make, things like that. But keep in mind that there are many reasons for doing doing this kind of estimation, and figuring out the total cost is only one of them. The other reasons for doing estimation are also things like to try and understand how close your projected levels of effort are coming to actual levels of effort, or how much your at what rate your cost is accruing as opposed to what the total cost might be. um, so for example, in some projects, money will be released over time as you achieve certain milestones, and so if your costs are accruing to the project faster than you're getting reimbursed, even though your overall cost might end up being less than or the same as um, what you estimated, you might not be getting paid on time to be able to pay the people on your team, for example. Um, um, so the identifying the metric that you're counting or measuring is an important thing to do when managing a project. And the way to identify the right metric is um, is done using a technique known as the GQM, or goal question metric approach. A paper on this approach has been provided to you as a reading assignment. But basically, the idea is this: when identifying a metric, before identifying a metric, identify what goal you want to achieve by measuring what it is you want to measure. Okay, so for example, if the goal is predictability, then what you want to measure is not size but variation. So what you want to measure is not the actual value of something, but how different the actual value um, is varying from the estimated value. And that becomes your question. So if the goal is predictability, then the question becomes, what is the variation between actual and estimate? And then that defines your metric, which is the difference between um, the actual value of something and the predicted value or estimated value of something. One estimation technique used a lot in industry, primarily in the military industry complex. So companies that they do a lot of contract work for the government and for defense, for the Army, Air Force, and the military, and so on. It's a technique known as the Delphi technique. Here, the assumption was that if you get a collection of experts, each with a different each with a different area of expertise, and you got them to estimate the size or the complexity of a problem, then even though the reason for the experts coming up with that opinion might not be clear, they would, in most cases, come up with accurate estimates. And if you allowed them to discuss their estimates with each other, their estimates would start to converge, and their converged estimate would be more accurate than if they simply went to one kind of expert, or if they used other techniques to estimate something. So the technique sort of works like this. A question is posed to a room full of experts, maybe 5 or 10, each from a different area. Um, this is done a lot in the military, for example. How long will it take to achieve X, either a political or a military gain? And they get a collection of experts, maybe from the Air Force, the Army, and the Navy, maybe from the CIA, maybe from um, those responsible for rebuilding, things, people like that. Get them in a room, pose the question to them, and they sort of write down the answer, and then anonymously, without any discussion. And then once their answers have been written down, they're put up on the wall, and then they're compared. and then the experts sort of discuss amongst themselves why there was variation in their estimates, why they came up with their estimates as opposed to what others did to come up with their estimates. And through this process of discussion, the idea is that the estimates would converge, and that this converged estimate was turned out to be reasonably accurate. And finally, here's an estimation technique, which is a parametric estimation technique. And this estimation technique is known as the UML, use case points approach. And this estimation technique is described in detail in one of the handouts provided to you electronically. So, look at the zip file for the resources for this project management module, and you will see a paper called Use Case Points and Estimation Approach. And here the idea was that the assumption was that you knew the number of use cases. You knew the use cases that were going to be implemented for the project. So you knew the use cases, you knew the actors. You also had some sense of the architecture. You had some sense of the skill levels and other environmental factors. Also, you had some idea of the technical complexity of the problem. And you put all of those into a formula and came up with an estimation for the for the system. So what was done was actors, use cases, the architecture, the technical complexity, skill levels, all were given a number. Then they were given weights, and then they were just basically plugged into a formula to come up with the estimate. In your project, I'm asking you to do an estimate based on use case points. I'm also asking you to do an estimate based on linear estimation, and I'm asking you to do them independently, so that you have two different people doing these two estimates, and then seeing how they compare. Now you might ask, in this use case points approach, where do the weights and coefficients come from? And to answer that, I point you back to to an earlier slide when I said all this comes from internally collected data. So you collect data and you perform regression analysis to figure out what these coefficients and so on are. So now let's look at agile project management. The first thing to know about agile project management is that there is a lot of planning in agile processes. It's a myth to think that agile projects are chaotic and there is no planning. Actually, as a matter of fact, there is more planning in agile methodologies than there are in structured methodologies. The real difference is in the purpose for which planning is used. In structured software methodologies, software engineering methodologies, planning is used to predict more than it is used to monitor, adjust, and manage. And with Agile, all of the planning, all of the project management is really used to monitor, adjust, and manage as opposed to predict. So to go further now, we will look at a flavor of Agile known as XP, keeping in mind that what we say about XP is actually true about most companies that follow Agile, because most companies that follow Agile have taken the best of a collection of Agile methodologies and unified them and brought them in and used them within their organization. And almost all companies use a collection of XP practices, or rather practices from XP, as a core part of their methodology. And in particular, from XP, the planning part of it is a core part of this unified Agile methodology that most companies follow. Anyway, so in XP, the planning process is divided into two stages, release planning and iteration planning. And you can think of a release as a large iteration with many sub-iterations within that. You can also think of an iteration essentially being a release. The only difference between a release and an iteration is that at the end of a release, software is actually given to a customer. At the end of an iteration, the software is not given to a customer. It is simply, you simply go on to the next iteration, and then you collect a set of iterations and combine them into a release. Okay. So let's take a look at release planning and iteration planning. You will see that all three of them, that both of them, release and iteration planning, consist of three phases. What is known as an exploration phase, where you try and figure out what needs to be done. A commitment phase, where out of all the things that need to be done, the team says, we will do this. And then a steering phase where the execution takes place, and then the project is monitored and then adjusted as you go along. So take a look at what happens in release planning and iteration planning on the slide. Just keep in mind that these are similar activities. The only difference being that releases are large in granularity, and what is done at the end of a release is released to a customer, and that a release is really composed of many iterations. But you can also think of releases as cycles, just as you can think of iterations as cycles. Let's look at the release life cycle within an agile process. So it all begins with, so if you remember when we did the requirements module in this class, that we said that agile methodologies use stories to collect requirements. Well, stories are when a project begins in the inception phase, when you're trying to figure out what the project is supposed to do at a high level, what the system is supposed to do at a high level, the stories you collect are actually high level stories. There might be a story entitled real-time customer support, or else another story that says role-based access control. Okay, as opposed to, and these stories are basically then taken and grouped into releases. So when a release begins, out of these high-level stories, the candidates for a particular release are identified. These stories are then refined and analyzed some more, and then broken down into a consistent granularity. The release is, so now we've gone through this exploration phase of the release. Remember, we talked about the release lifecycle as having an exploration phase. The next phase after that is the commitment phase, where the team says, okay, this is what we are going to do in the release. That is the commitment phase. And then the release is developed. And to see how a release is developed, you have to look at the iteration lifecycle, because, like I said earlier, releases are composed of multiple iterations. Then finally, the release is put together for testing. The customer signs off on it, or decides that the release is not ready for release, and so there's a go or no go decision made. And if it's a go, then the release is deployed, and then the similar process is followed for the next release. And this slide captures how an iteration life cycle takes place. So the stories for that release have been identified as part of the release planning. Out of those stories, you pick the ones that you're planning to do in this particular iteration. You break down the stories further so that you can, they are down to a granularity where somebody taking a look at them can say, yes, I think I know how to implement this. You expand the narratives on the story. You expand the story so that all the details are filled in. You have your iteration planning meeting. Your team says, okay, these are the stories that I'm going to do for this iteration. You develop the iteration, rather code and build the iteration. You test the iteration. You show it to the customer. The customer says, okay, these stories have been implemented. These stories have not. There might be changes that change requests that are identified, that are captured, and then you do a debriefing or a retrospective on the iteration, and then go on to the next iteration. So this slide is basically showing how, in an agile methodology, how the agile methodology fits into the various stages of software development. The inception stage, the elaboration stage, the construction stage, and the transition stage. So you will see that initial grouping of stories into releases sort of is the inception phase. Then within the elaboration phase, the important stories are implemented in iterations. The iterations take place. At some point, all the risks get resolved within the project, So then you enter the construction phase where you're simply adding features, and then as the release ends, it's handed over to the customer, and that's the transition phase. Now, one term that that we haven't introduced earlier is the term known as a spike. So a spike is a story added not by the customer, but added by the development team because of a perceived risk that they see in the project. So for example, let's say um, um, somebody in the development team says, hey, you know what, I haven't figured out how floating point calculation works in C++, and that's an important part of our system because we use floating point calculation to do all our actuarial analysis. Let's say that this is a application developed for the insurance business. So a technical spike would be added by a developer to go and investigate how accurate floating point calculation is in C++. Note that a tech spike is not a story that came from a customer, so it has no business value. A tech spike is a story added by a developer in order to resolve a risk. This chart is a typical chart used in agile, used by an agile team to track progress. It's called a burn down chart. The x-axis are dates, and the y-axis are what are known as story points completed. So the blue line there shows how many story points are left over at the end of that particular time period. So you started off with 64 story points. At the end of some time period, you ended up with 56, probably at the end of each iteration. At the end of the next iteration, you ended up with 48. At the end of the next iteration, you ended up with 40, and so on and so forth. That's how you planned for your story points to be implemented. And your actuals actually are shown in red. So you started off not with 64, but with 72 story points. At the end of the first iteration, you could only do 2.5. So you ended up with 69.5. Then at some point you had a huge productivity improvement, and then your actual sort of came closer to the plan, and so on. Yeah. So this is a typical chart used in an agile methodology. It's meant to be put up on a wall so that it's highly visible. High visibility being a big principle inside agile, and it's basically used to monitor a project. This is a similar chart known as a burn up chart. So rather than counting down from what you have in your in terms of requirements or stories to implement, you're counting up. So the pink line there is the amount of stories you have to implement, and the blue line there is the number of stories that you have implemented at each iteration. And you see that as you implement more and more and more stories, the blue line starts catches up with the pink line, and when the two meet, the project is considered over. This slide captures the typical learning that occurs after students have done the Agile Bootcamp or the Fun with Legos game. And we will cover all of these as a retrospective at the end of the Agile Bootcamp workshop that's coming up. Just take a look at this. These are sort of what we expect you all will learn from that game. And if you see the slide after doing the game, you can confirm that these were the things that you learned through the game. So we will close this this agile versus structured estimation with a slide on the differences between the two approaches. So keep in mind that the goals of estimation in agile are monitoring and management rather than prediction and budgeting. Okay, so the whole idea is you work for a fixed period of time, you get a sense of what you can do there, and use that sense to estimate how much you can do in the next iteration, and so on and so on. And the idea is to get consistency rather than accuracy. So the units don't matter. The units don't have to be in hours, minutes, days, whatever. They are in something known as story points. And the idea is you want to do a consistent number of story points in each iteration. You will also see, and once again, you will see this in the Fun with Legos or Agile Bootcamp game, that estimation is not done in absolute terms, but in relative terms. So you're estimating which use cases are larger and which use cases are smaller, or which requirements or stories are larger and smaller, rather than exactly how long implementing a particular use case or story might take. And this estimation is done in a relative manner as opposed to an absolute manner. And the estimation is done in these sizes, in these arbitrary units, rather than in something like person hours or effort or anything like that. Oh, and one more thing. In most cases, these sizes are not developer efforts, but the sizes are really proxies for business value. So the idea is you're asking the development team, how much business value can you consistently deliver in each iteration? And you're using that quantity to sort of understand how much value the project will deliver in each iteration, and therefore over time. The next module in this section on project management is a module on what is known as risk management. Risk management is a very, very important aspect of software development, and we will see what risk management is, what techniques can be used to manage risk, et cetera, in this section of this module. So this slide basically tries to describe or define what a risk is. So a risk is a possible future event that will lead to an undesirable outcome. It is a problem yet to occur. So it has not happened yet. It's not a problem yet. It is something that might occur. Okay? Incidentally, you might even have risks stated as requirements, which is as a non-functional requirement, you might have a requirement that says this product shall achieve market acceptance. That is not a feature of the product. It is really a risk of the project. And you might see it that way as well. So a risk is a problem yet to occur. Yeah? Risks become problems at what are known as risk transition points. And often there are transition indicators that will indicate that the risk is likely to become a problem. So for example, let's assume that the risk is, let's say you have a farm and you're planting some crops, and the risk is that you might have a thunderstorm that might blow the crops away. Okay, so the risk is the risk of a thunderstorm. The transition point is when the thunderstorm actually starts and the water and the rain starts falling and washing your crops away. And the transition indicator is the clouds forming over your land. Yeah? Hope that makes sense. So you can look at a transition indicator and realize that the risk is likely to become a problem in the near future, or is going to become a problem in the near future. When it does become a problem, that's a risk transition point, and now that risk has become a problem. So now that you know what a risk is, what is risk management? So risk management is the process of dealing with risk by quantifying uncertainty and then dealing with it in a systematic manner. Okay, so all companies should do risk management. All organizations should do risk management. The reasons for doing risk management is you can't simply rely on positive thinking. You can't always avoid risks. If you do risk management systematically and it becomes part of your company culture, it makes genuine risk taking possible. And keeping in mind that it is risk taking that enables personal and business growth. Without taking risk, you cannot grow. And what risk management then does is it makes risk taking possible because it brings it out into the open. It puts a systematic intellectual framework around it. It decriminalizes it, and it basically makes it part of the culture, so that it is done by everybody in a free and natural manner. The other thing that risk management does is that it bounds uncertainty, and we'll talk about how it does. And essentially what risk management does is that it mitigates blindsiding and focuses attention where needed, rather than focusing worry where you might not know. Rather than creating worry, it focuses attention and allows you to control your destiny as opposed to being bound by it. Many organizations don't do systematic risk management, primarily because they're not mature enough, but also because they might not have enough data. They're too new. Um, it's possible that only one person in the organization is doing risk management. It's a he ends up being branded as the naysayer, the person who's always bringing up the bad things that can happen, um, or else the 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 risk is so small that you don't have to manage it, or the consequences are so great that there's nothing you can do about it. If any of these things are true, then organizations and people will not do risk management. We said that risk management is the process of dealing with risk by quantifying uncertainty. So what do we mean by quantifying uncertainty? And we'll give you two ways by which, or two um, views of quantifying uncertainty in a software project. Okay, so this is a graph that is known as um, as a risk curve, and the x-axis on that is time, and the y-axis on there is the relative probability that the project will complete on that particular date. Okay, so the idea is that the project will complete somewhere between January 1st and December 31st, and the graph basically shows the probability that it will complete on any of those two dates and the dates in between. So January 1st is known as the estimated date. So this is the date that when the project started and an estimation was created, this was the date at which the project manager said, this, based on the estimation, this is how long it would take. And the point being made here is that the probability that the project will actually complete on the date that it was estimated to complete at the beginning of the project, this probability is 0. In other words, there is no way that this project will complete on the date that it was estimated to complete. Okay, and here's why. If you remember back to the estimation slides, we said that people are pretty good at estimating what they do know. So if you think of a project and think of all the components that go into implementing that project, and then estimate each of them and add them up and so on, and you come up with a date, that date is likely to be correct, assuming that when you actually do the project, it's exactly those components that go into the project. What will typically happen is that there will be unknowns that will creep into the project, and therefore the estimation, the actual time for doing a project will always be greater than the estimated time. So the date that the project will finish and the date that you estimated it would finish, this probability is 0. Okay, so let that date be Jan 1st. So as you progress further away from January 1st, let's say February 1st and March 1st and April 1st and May 1st and so on, you will see that the probability that the project will complete during those dates will increase. It'll be more than Jan 1st because you'll have more time. Okay, and then as you stretch further and further out into the future, the probability that the project will complete on a date, say December 31st, will become 0. That is, there is a 100% guarantee that the project will complete before December 31st, which means that the probability that the project will complete on December 31st is 0, because there is a 100% certainty that the project will complete before then. Okay, hope you're understanding this. Basically, we are saying that if January 1st was the date that the project was estimated to complete, the probability that it will complete on that day is 0, right? And if you look further out into the future, at some point you'll reach a date by which the probability that the project will complete on that date will also be 0, because enough time will have elapsed and the project is certain to have completed. Okay, does that make sense? Hope that makes sense. Anyway, and in between you have a graph that shows the probabilities in some sort of a shape that shows the probability that the project will complete on that date, somewhere between the first date and the last date. So this is the same graph, except that we have plotted cumulative probabilities. So the earlier graph had the probability that a project would complete on a particular date. Okay, the probability that it would complete on that particular date. This graph is the probability that a project will complete on or before a particular date. So this is a plot of cumulative probabilities. It's the integration of the previous curve, okay? And you will see that because, ultimately the cumulative probability will be, should add up to 1 or 100%. You will see that this graph will start off at 0 and then go up to 1, okay? Now here's the second way of quantifying uncertainty in a software project. Think of the software project or the software system being represented in terms of versions, where each version is a collection of features, and where each version with a higher number includes all the features in a lower number. So in this graph, V12 is a version with a certain set of features. V21 is another version with a collection of features that include all the features in V12. V23 contains all the features in V21, and V27 contains all the features in V26, 25, 24, 23, and lower. Okay. In this graph, in the previous graph that you saw, the x-axis was the date, and the y-axis was the probability. In this graph, the x-axis is the version. The y-axis is the probability, and the entire graph is for a particular date. So the graph represents the probability that a particular version will be available on a particular date. Let me repeat that. This graph gives you the probability that a particular version will be available on a particular date. Okay. So let the date for this graph here be, I don't know, February 15th. Then what is really being plotted here is that the probability that you will only get V12 in this release is 0. And the probability that you'll get as much as V27 in this release is 0. But you're likely to, you're very likely to get V23 as part of this release. You're less likely to get only V21 as part of this release, and so on. Okay. So once again, this graph is for a particular date. The date is fixed, and the graph is of the probability of getting a particular version on that date. Okay. So basically, this quantifies risk, because when if the customer comes to you and says, I'm sorry, we have to have a software release by this particular date, you can tell them, okay, great. I won't negotiate with you in terms of dates. Instead, I'll negotiate with you in terms of versions, okay, in terms of functionality. If you want it on this date, there's a high probability that you will get this set of features. There's a slightly less probability that you'll get this set of features, et cetera, et cetera. Okay. Hope that makes sense. If you have any questions, please ask in class. So once again, what is risk management? We defined it as dealing with risk by quantifying uncertainty and then dealing with that uncertainty. Okay. So let's talk about all the various strategies for this last part, which is dealing with risk. So the first question is when to assume risk. And the principle here is you only assume great risk if the rewards are equally great. In other words, you don't do a project that's highly risky where the deadlines are extremely tight and it's very unlikely that you'll ever meet them, unless that project has incredible potential and can generate a lot of revenue or profit for the company. In other words, don't take on risky projects with no value. Okay. The risk that you take on must be offset by the value you're likely to create. Okay. Second thing is how to assume risk. So don't simply take on the risk and then worry about it. Yeah. Deal with it by presenting all commitments not as single points. I will release the software by this date kind of thing, but as risk, but as risk diagrams or risk curves. Say, I can release this project within this window. Here are the probabilities. Or if you give me a particular date, here are the features that I could have by this. I could have in the software, and here is the probability that And here's the probability that these features will be there. Okay. Second thing is define benefits to the same precision as costs. So for example, if your customer asks you to quantify your costs down to the last dollar, he needs to present benefits quantified to the last dollar as well. If your customer can only quantify benefits in terms of ballpark figures, he should be okay with you being able to quantify costs in ballpark figures as well. Okay. Make clear that goals are not the same as estimates. So, for example, if if he asks you for a date and you give the date of March 15th, make sure that your customer understands that March 15th is a goal, not an estimate of when things will be completed. So you're shooting for March 15th, but you're not likely to complete it on that date. Okay. The fourth thing is, this is a complicated statement. Make sure closure metrics are defined before the first 15% of the project is completed. But it's actually something very simple. It really means, people take on projects without really knowing what they're about or what it's going to entail or what the benefits are and so on. Okay, that's all part of doing business. Okay, you don't know everything when you begin a project. Columbus did not know that he was going to discover America when he set sail from where he set sail from. However, by the rule of thumb is, by the time the first 15% of the project time is over, you must know what the problem is and how you're going to solve it. In other words, the elaboration phase of the project must be done by the time you've completed the first 15% of the time allocated to the project. Okay, so that you have enough time to deal with any risks that can take place. Okay, so you have 85% of the budgeted time left to deal with any problems. Okay, in other words, there should be no assumptions, uncertainties about what the project is supposed to accomplish after 15% of the time that has been allocated for the project is over. Okay, this is just a rule of thumb, 15%, but the basic idea is know where you're going by the time you've completed 15% of the journey. Okay. The third thing is you have different strategies for dealing with risk. The first strategy is risk evasion, okay, which simply means burying your head in the sand and assuming that the risk is not going to become a problem. Okay, this is not a strategy, obviously. This is just luck. The second strategy is what is known as avoidance, which is don't take the path that is risky. So, for example, if a project is really, really risky, don't do the project. Or if using a language that nobody understands or nobody has experience with, or using a enterprise application framework like, say, .NET, when nobody knows how to use it, is a risk, then simply don't do that. Implement it using something you do know. Okay, this is risk avoidance. The third one is risk mitigation, which is do things that will over time reduce the risk. Okay, so for example, let's take the same problem, which is you're asked to do the project using .NET, and it's a risk because nobody in your team has any knowledge of .NET. Risk mitigation is, for example, training the people in .NET before taking on the project. Yeah, expending cost in reducing the probability of the risk or the extent of the risk is known as risk mitigation. So for example, you could have two teams, one that does it in .NET and one that does it in J2EE, with the idea that if the .NET project fails, then at least you have the J2EE one. Okay. The key thing about risk mitigation is the following: you're expending additional cost to reduce the likelihood or contain the damage due to any risk. Okay? I hope that makes sense. It isn't avoidance. You are taking on the project, but you're doing something more. You're expending additional costs to make sure that the risk is either less likely, or if the risk does happen, there will be less damage or less cost. Okay. The fourth strategy is what is known as risk containment. Okay. So for example, let's take the same issue about doing the project in .NET. Maybe you could do just the user interface portion in .NET and do the rest of the project in Java or J2EE. Okay, that way you've contained the damage of not knowing .NET, contained the damage of the risk of not knowing .NET to just the user interface portion of the system. So here's the process that companies follow as part of risk management. Okay, so this is a standard process. It's part of best practices, and most mature companies will follow a process similar to this. So when a project starts, as they do their estimation, they will get the team together and have a brainstorming session that tries to brainstorm catastrophic outcomes. Outcomes such as we are unable to complete a particular component in time because nobody knows .NET, or a bug is reported in a particular component and nobody has the knowledge to fix it. Okay, keep in mind that these what is being brainstormed here are not risks, but catastrophic outcomes, the things that can go wrong with a project. Okay, the events that can go wrong with the project. Then the idea is to take these outcomes and then come up with scenarios where these outcomes might happen and identify the root causes of these outcomes. So for example, take the situation where a bug is reported on a component and nobody knows how to fix it. The scenario, so you come up with a scenario for this and then identify the root cause, which is the person who wrote that component has left the company. Okay, so the risk is a personnel transition or a personnel or a person basically leaving the company. Okay, that is the risk. Okay, then find a transition indicator. So what might be a transition indicator for the person leaving the company? The transition, of course, is that the person leaves the company. What might be an indicator? The indicator might be the person is showing signs of discontent. The person is, you track the person's web browsing and find he's visiting a lot of employment sites like monster.com or dice.com. Those are all the transition indicators that might indicate that that person is likely to leave, or a person getting tons of recruiting calls. Okay, so once you find that transition indicator, you know what to monitor. Okay, then you basically estimate the probability that the risk might become a problem. You estimate the impact of that problem. You estimate how much budget you might need to deal with that problem, how much additional time you need to deal with that problem. And whenever you run into a situation where you have unknowns, you and your team basically will brainstorm, what could I know? Okay, what could I know that I don't know now that will help me bound this problem? Okay, so once again, take the situation of the person leaving. You might initially just throw up your hands and say, I don't know when he's going to leave. And then you could start thinking about how you might find out that the person is likely to leave. And you might realize that his web browsing activity, monitoring his web browsing activity and whether he looks up Monster and Dice and so on, might be a way of figuring out whether that person is going to leave. So that, basically when you run into an unknown, you try to think through what is it that you might have known that if you knew it, it would help you address that unknown. Okay. Then you describe your management actions, which is how are you going to deal with it. So coming to the situation of personnel turnover, or somebody leaving, your management action might be don't put that person on the project team if you know that that person is likely to leave, or else train an understudy. So whatever this person does, you have somebody working with him or her, so that even if one of them leaves, the other one is ready to take over. Things like that. The next one is an interesting one, which is risk assignment, which is and the best a good example of why you might do risk assignment is an example like this product or this software application must get market acceptance. The development team could look at that risk, which is the risk of market acceptance, and say, this is not our problem. This is a problem of the marketing department or the organization that is commissioning this product, not us. Okay? Essentially, they have taken the risk and assigned it to somebody else, presumably higher up in the food chain, who can deal with that risk. So, because it is not appropriate for that risk to be dealt with at your level. Okay. And the other thing is that there are certain risks that you can't mitigate, a lightning strike or or nuclear war that you can't mitigate. These simply are, these are showstoppers. Okay, the company goes out of business. Okay, things like that. These are showstoppers. There's nothing you can do about them. Okay. For such things, you don't try to do risk management because there's nothing you can do. Instead, you simply document that as those as assumptions. Okay, this project will succeed if the company stays in business. Things like that. Okay. Once you've done risk assignments, you add this risk to the risk repository. Basically, you've brainstormed a risk. You decided that this risk was new, and you add it to a database of risks. Okay. And incidentally, this database doesn't start with an empty data. You don't start with an empty database at the beginning of each project. You look at the previous projects that have taken place. You see what risks occurred with, what risks were considered and or became problems in those projects, and you populate your risk repository or risk database with all those risks. Okay. And incidentally, if you discover a new risk, you populate that database with it. So you have a database or a library of risks that you can then take to that you can then analyze at the start of every project and say, is this project likely to encounter any of these risks? So basically, you have some past experience to do your risk management. Okay. And then once this is done and the project begins, well, you continue the risk discovery and the monitoring of the transition indicators and the risk management and so on for the life of the project. You're basically kicked into your day-to-day managing of the process and of the project, and as part of that day-to-day management, you're doing risk management as well. Just keep in mind that as you make progress in the project, as time evolves, the risk profile, which is what risks are likely, how likely they are, what impact they might have, and so on, will change over time. So the impact of somebody leaving early in the project might be low, but it might be high once the project is 3/4 of the way through, or it might be the reverse. Once you have your architecture in place and you're in the construction phase and everybody's just developing new features, the risk that your project manager or your lead architect may leave may be low, because even though the probability might be high, the impact of that risk might be less than what it might have been if that person left in the middle of the elaboration phase when the architecture was still being developed. So the previous slide talked about a budget and a schedule reserve. What are they? Basically, it's extra money in the budget to spend in case you run into a risk. What is that is budget reserve, and extra time available to the project to deal with any delays that might take place. That is schedule reserve. Okay, so if you have a curve that shows how much money is being spent over time, so time is the x-axis and money being spent is the y-axis, then you see a curve like that, like the lower black curve. Then when you have a budget and a schedule reserve, you have the thinner higher curve, which basically says if you needed to, you could spend money at that rate and you could have some extra time to finish the project. And this graph talks about the impact of risk mitigation on budget and schedule reserves. So I hope you remember what risk mitigation is. It is additional actions you do to reduce the probability of a risk or reduce the impact of a risk. So this is additional cost you're expending in order to reduce the risk. Okay, so you can see that when you start doing mitigation, the cost of a project is always higher than if you don't do mitigation. But the idea is that the impact of the risk will be lower, and the amount you have to have as reserve in terms of budget and time will be less because you're doing these mitigation activities upfront. So now that you've understood sort of the principles behind risk management, let's take risks in software projects. Okay, so software projects have what are known as core risks that all software projects will have, and then they'll have risks that are specific to a particular project. So there are 5 core risks. Schedule risk, which is the project will be delayed and will not come under schedule. The risk that requirements will increase. This is known as requirements creep. The risk that there will be personnel turnover. the risk that the requirements are not correctly translated into specification. So the requirement didn't change, but the project team didn't quite understand it, that specification breakdown, okay? And then finally, underperformance and, and incompetence on part of the team. Incidentally, these risks are somewhat in order. So in most projects, the risks are not lack of ability of the team or lack of commitment or motivation of the team. Even though in most projects, people will blame the project team for failure, history has shown that underperformance and incompetence is the last reason why projects fail. They fail for the other 4 reasons, okay? And this slide basically says the following. When you begin a software project and as you progress through it, take these core risks, or what we are calling causal risks, examine the kind of project it is, add risks that are specific to that project, and when you put those two together, you get what are known as the aggregate risks. And these are the risks that you have to manage. So here we are at the end, and this is your review slide. So basically, based on all the slides that you've seen and looking at all the activities in project management, which were planning, organizing, staffing, leading, controlling, and coordination, reflect back on what we've covered. Think about how structured processes deal with all these activities, how agile processes might deal with all these activities, and how you can, how what role risk management plays within these project management activities.